So we are back at the compound for an example. Remember, this is the time to create and build a strategy to approach problem. You want to complete the problem with me, and then think of a way to approach the problem that will make it easier for you as well. So the plan is to gather all expressions, relationships, understandings, or assumptions and bring them to the table. This question says calculate the pH, and they want us to calculate the pH with 3 different scenarios. First with this buffer solution, then when this buffer solution has NaOH added to it, and then when this buffer solution has HCl added to it. And so that's going to be a lot for us to be involved with. We first have to get our overall Rice table just for the initial amount. And then after we add NaOH, we have to have a Rice table to get our new initial amounts. And then finally, we're going to use a brand new Rice table with our initial routes to get the pH that we're looking for. Finally, in part C, we're going to, of course, use our initial amounts that were in part A, and then we're going to get brand new initial amounts after we add our HCl. Once we get our brand new initial amounts, we're going to use those amounts to find pH. And so yes, there's going to be a lot of Rice tables that we have to go through. First, let's start off with letter A. Letter A says, calculate the pH of a buffer solution consisting of 0.50 molar HClO. It gives us a Ka value of 2.9 times 10 to the negative 8. And 0.60 molar NaClO. And so because we're dealing with the buffer, we definitely want to identify our conjugate acid-base pair so that we can get our reaction for letter A's Rice table. So we know we're going to be dealing with a Rice table. At least there's only one for letter A. Again, we have our weak acid here, so that's HClO. We're going to mix that with water. It's going to be in equilibrium to form what? We know it's going to form H3O plus, right? And it's also going to form its conjugate base, which is ClO minus. And so just knowing that this weak acid and how it mixes with water gives us these products is going to help us be able to look at this salt here, this soluble salt, and say, okay, this is going to dissociate to Na plus and ClO minus. And this ClO minus is the conjugate base of this weak acid, okay? The Ki value also, we can use an assumption here because it is times 10 to the negative 8. We know we can get rid of that minus X amount because it's going to be negligible, okay? Also, since we have a Rice table, we can get rid of water here. Okay, so we fill out our Rice table. I have my initial amount for HClO. I have my initial amount for ClO minus. I know my H3O plus is going to be 0. It is a product. And then my water, as we see, we do not use, okay? So for HClO is going to be used up. It means it's going to have minus X, and both of my products are going to be plus X. We have 0.50 molar minus X here. And again, we said we can make an assumption here. With our Ka value, so we can get rid of that minus X. We also have the X value for H3O plus, and also we have 0.60 molar plus X for our ClO minus, or our conjugate base. We also can get rid of plus X here because we again made that assumption based on our Ka value. Then we can say our Ka value is equal to H3O plus times the ClO minus divided by HClO. And this entire thing is equal to 2.9 times 10 to the negative 8. And of course, I'm now going to say, okay, I know what my H3O plus concentration is. That's going to be X. I know what the equilibrium amount of ClO minus is going to be 0.60 molar, and HClO is 0.50 molar. So now I'm going to take all this and rewrite it so it can continue to be organized, okay? Okay, so I have it reorganized. Ka is equal to X times 0.60 molar divided by 0.50 molar is equal to 2.9 times 10 to the negative 8. Now, normally what we would do, we would solve for X. Why? Because X is equal to our H3O plus concentration. We saw that, right? We just saw that. And so what else or how else can we rearrange this? Well, when we looked at our buffers in our previous discussion, what did we say? We said our H3O plus is equal to our Ka value times our weak acid, okay, which is going to be our HClO, the concentration of that divided by the concentration of the conjugate base. And so I can also use this to solve for X as well, making it easier for myself just by using the ratio. So that's what I'm going to do here. Another color, and I'm going to just basically fill out my Ka and my ratio here to get my H3O plus concentration. Okay, so I'm going to have my Ka, which is 2.9 times 10 to the negative 8, multiplied by my HClO amount, which is 0.50, divided by my ClO minus amount, which is 0.60 molar, okay? And then that means my H3O plus concentration is going to equal to 2.9 times 10 to the negative 8 multiplied by 0.833. And this is equal to 2.4 times 10 to the negative 8 molar. That is the H3O plus concentration. And so therefore, if I go ahead and get my pH, I can say my pH is equal to negative log of my H3O plus concentration. And when I do that, I get negative log of 2.4 times 10 to the negative 8 molar is equal to a pH of 7.62. So for letter A, the pH of this buffer solution is 7.62. Now, for letter B, it says, okay, we have a buffer that's 7.62. Well, what happens when we add 0.020 moles of NaOH to 1 liter of the buffer solution? Well, first things first, we have to recognize what are we adding here. Well, we know that NaOH is going to disassociate completely to Na plus and OH minus. What else do we know? We know that we're going to assume that the NaOH that is added, or really the OH minus that is added, is going to be used up completely, okay? Because it's going to be used up completely, that's going to allow us to solve for X, or the equilibrium amount, and automatically get our new initial values for a brand new Rice table. Okay, folks? Another thing is, since we're adding 0.020 moles of solid NaOH, we need to make sure that we put this into molarity. We need to get the molarity of the OH that we're actually adding, okay? And so we have to do a couple of calculations. First, I always say, let me get the molarity to see the exact amount or concentration of OH I'm adding in. And then I'm going to set up a Rice table and basically say, okay, this OH minus, which portion of my conjugate acid-base pair will react with the OH minus? Whatever portion reacts with it is going to give me the reaction for my Rice table, okay? And so since we have OH minus, we know that the weak acid is going to end up mixing with our OH minus there. And so to help us get our new initial amount, we're going to take OH minus, mix it with the weak acid, get our products of water and the conjugate base, and then of course we'll be able to go from there. Okay, so I want to focus on the added OH minus. They gave us 0.020 moles divided by 1 liter, and so the concentration of added OH minus is 0.020 molar, okay? So I have my initial amount in my Rice table. Remember, since we're adding a base, we must have the weak acid that's going to be able to use up that base. So we have our weak acid, which is HClO, mixed with OH minus, is going to go to completion to form ClO minus and, of course, water. So our initial amounts are already given from part A of 0.50 here and 0.60 here. Our initial amount of OH minus we just found of 0.020. Now, this is where we have to kind of have a little bit of understanding about OH minus being used up and this reaction going to completion. If we know that OH minus is going to be used up, that means the equilibrium amount is going to equal to 0. And so I know my initial amount is 0.020 molar. That means I'm just solving for X. And so X is also going to equal 0.020 molar. And so then I can basically substitute X in every single portion of the equation here. So now for OH minus, if I already know it's going to be used up, I don't have to focus on the equilibrium amount there. But to get the equilibrium amount of my weak acid here, I'm going to take 0.50 minus 0.02, and I get 0.48. And then I'm going to get the equilibrium amount of ClO minus, or my conjugate base, and that is 0.60 plus 0.02, which is going to give us 0.62. And now I've effectively got my new initial amount from this Rice table of my HClO and my ClO minus. So what do I have to do? I have to create a brand new Rice table with my new initial amount in equilibrium, right? So that I can get the pH like the question asks. So that is the next part. Some folks might say, well, how do I know what my reaction is going to be? Look no further, folks. We already got the reaction for this. The reaction is going to be based off that Ka, which is going to be your HClO mixed with water in equilibrium to form ClO minus and, of course, H3O plus, okay? Now, when we complete this Rice table, we can go ahead and find our H3O plus value and then use that to find our pH. So we set up our Rice table. We have our HClO mixed in water to form our conjugate base and, of course, H3O plus. We already have our new initial amount after we've already added that NaOH. Now, our new initial for this is 0.48. Our new initial for this is 0.62. We know this is minus X. Water doesn't mean anything. We know this is plus X and plus X. Everything's in a 1-to-1 ratio. Everything's already in already balanced, okay? Now, to get our equilibrium amounts, we're going to take 0.48 minus X, 0.62 plus X, and of course, our X value is simply going to be equal to the H3O plus concentration. Now, what do? Well, guess what, folks? We are still going to be using the Ka value from letter A, okay? So from letter A, our Ka value is 2.9 times 10 to the negative 8, meaning we can make an assumption. So I can get rid of this minus x here, and I can get rid of this plus x here. Okay, so again, you can have your Ka is equal to 2.9 times 10 to the negative 8. Our products are still going to be the same, ClO minus and H3O plus. And of course, our reactant is still going to be HClO. We're going to do the same thing. We're going to solve for our H3O plus using our ratio. Okay, so let me go ahead and get rid of that and show you what to do there. Okay, we set up our H3O plus is equal to Ka times our ratio here. So we get 2.9 times 10 to the negative 8 multiplied by the concentration of HClO, which is 0.48, divided by the concentration of ClO minus, which is 0.62. This, when you divide it, is 7.7 times 10 to the negative 1. When I take my 7.7 times 10 to the negative 1 and multiply by 2.9 times 10 to the negative 8, I get an H3O plus concentration is 2.2 times 10 to the negative 8 molar. The final thing to do is to get our pH. And what do we get? pH is equal to negative log of 2.2 times 10 to the negative 8. And therefore, our pH, after we added 0.020 molarity of NaOH, was 7.66. And so our original pH was 7.62. And after adding the strong base NaOH, it only increased to 7.66. That's still very, very slight, not even a full pH unit. And so as you can see, this type of problem is extremely involved. Will you ever be given this on an actual exam? Of course not, right? It's too involved. And as we go along, we're going to learn a way to make this process go faster using a brand new equation. So just wait on that, right? Now let's go ahead and get into part C. We're going to do the same thing. We got to figure out how much of the HCl is added. Then we got to do a Rice table to show and get brand new initial amounts. And then we got to do a final Rice table to get the H3O plus concentration. And of course, go further and get the pH like the question asked. Now for letter C, they gave us a volume and a concentration of HCl that they're going to be adding. And then they gave us the volume of each component that's in the overall buffer solution. And so therefore, if we're given a concentration and a volume of one species, and then we're given the volume of another, we can go ahead and use the dilution equation to find the concentration of course, whatever other species that we're looking for. So for us, we're adding HCl. It's 30 mils of HCl that we're adding to a 0.50 liter buffer solution. So once I convert my 30 mils to 0.03 liters, and I add it to 0.50 liters, I get a volume or overall volume of 0.53 liters in total, okay? Using the dilution equation, M1V1 is equal to M2V2, if I solve for my second molarity, I can get the concentration of HCl added. I can get the new initial concentrations of HClO because that volume change is going to change the overall concentration. And then, of course, I can still get the same for the conjugate base. So I would just set up this overall equation here. Molarity 1 times the volume 1 divided by the volume 2 is going to give me molarity 2. And so for HCl, I have 1.5 molar that I started with times 0.0300 liter that was given divided by the total volume. And so the concentration of HCl added is 0.085 molar. We'll do the same thing with HClO, which is our weak acid. The initial amount was 0.50 molar. The amount and volume for the buffer solution was 0.50 liters. I'm going to divide that by the total amount, and I get a new initial amount of 0.47 molar. Same thing with ClO minus. I'm going to take 0.60 molar, which was given, multiplied by 0.50 liter, divided by the total amount of 0.53 liters, and I get a new initial amount of ClO minus as 0.57 molar. So we had to actually get brand new initial amounts right off the bat, and now we're going to continue to a Rice table to get our initial amounts after the H3O plus was added from HCl. And then, of course, we'll go further to get our pH. So this one, we had an additional step. As you can see, probably the longest example we've ever seen, right? But I want to make sure you get this part down because it does break out and give us an example of what we already seen through the lecture component. So we have our Rice tables. Okay, we have our initial amounts of 0.57, 0.47, and 0.085 that we just calculated using our dilution equation, okay? We know that our reactants are being used up, so we have minus x, and plus x for our product. Of course, we have 0.57 minus x here. And again, our H3O plus is completely used up, so it's going to be 0 at equilibrium. Therefore, we can automatically say our x value is 0.085. That's going to allow us to get brand new initial amounts for ClO minus and brand new initial amounts for HClO. Now, don't forget our reaction. You have to ask yourself this question. What is going to use that H3O plus and, of course, cause it to come out of solution? The only thing that's going to be able to use up this H3O plus and cause it to come out of the solution is going to be the conjugate base. That's why my reaction is ClO minus plus H3O plus to form HClO and water. The exact opposite of what we saw in letter B, right? So we fill out our Rice table. We know what the X value is. My brand new initial amount for ClO minus is 0.48. My brand new initial amount for HClO is 0.56. Now I'm finally to my actual final Rice table here. I'm going to take my weak acid and mix it with water, so we're back in equilibrium to form ClO minus and H3O plus. Once I know my H3O plus, I can go ahead and get my pH, right? So I have my 0.56, which is our new initial amount, and my 0.48, which is my new initial amount. I have minus X here, plus X, and plus X. Our Ka value is still something that we can use an assumption for. So I can get rid of minus X here, and I can get rid of plus X here. That means I'm going to have Ka is equal to 2.9 times 10 to the negative 8, which is going to be equal to my 0.48 times my X divided by 0.56. And we know we're going to solve for X or the H3O plus concentration and then simply get our pH. Okay, so solving for H3O plus, I get Ka times my ratio of buffer components. So it's going to be 2.9 times 10 to the negative 8 multiplied by 0.56 divided by 0.48 ratio. This ratio is equal to 1.2. I'm going to multiply that by my Ka value, and I get an H3O plus concentration of 3.4 times 10 to the negative 8. If I want to get the pH, I'm going to take the negative log of 3.4 times 10 to the negative 8, and I get a pH of 7.47. So the pH here is equal to 7.47. Our original pH was 7.62. When we added HCl, it went down to 7.47. Still not even a full pH unit. And so this is a complete picture of how we can do calculations based on buffers. All right, folks, a lot going on. And the next conversation, we're going to see how to simplify this process, something you will see on an exam. And some folks might say, well, why didn't we have to focus on volume for part B? Well, we do have this little part here that says in part B, assume that the addition of NaOH causes negligible volume change. So there's nothing to focus on there, okay? Remember, for me, I didn't kind of see that little part beforehand to add that in there, but I did want to add that here on the end so that there is no confusion. Part B, they specified that we did not have to focus on volume change. Part C, we did have to focus on volume change. All right, folks, let's go ahead and get into our next conversation.